Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be showing how to calculate the delta G of a reaction under non-standard conditions. So what do you do when you're given conditions that are non-standard? So here's the situation. Here's a problem we're going to be given. So here is an equation. Here's a reaction. You have 2 moles of NO gas plus 1 mole of oxygen gas, and it gives 2 moles of NO2 gas. And they're giving you the standard change of free energy for this reaction is negative 71.2 kilojoules. That would be under normal conditions at 25 degrees 25 degrees Celsius, 298 Kelvin. And so now we're given these new conditions, and so these are non-standard state conditions. And so we want to know what is the delta G of the reaction under these conditions. And so what we're going to be doing is we're going to be using that equation, delta G of a reaction is equal to the standard delta G of a reaction plus RT times the natural log of Q, where Q is our quotient that we've used before. And so to find Q, basically, this is an equilibrium quotient here. And so we need to find Q, the reaction quotient, and we're going to do that like before. So we're going to have the products over the reactants. In this case, we're going to have pressures of products over reactants. And so that's going to be the pressure of NO2 squared, because it has the 2 coefficient there, and then this is on top, and then these are on the bottom. You have the pressure of NO. Again, that's going to be squared because it has the 2 coefficient, multiplied by the partial pressure of oxygen. Okay, and so all we need to do is plug in the atmospheres that we have. And so we have the pressure of NO is 0.1, so 0.100 atmospheres squared over the, sorry, that should be NO2, wrong one. So NO2 is here, so that's 2.00 atmospheres squared. And then we have NO squared, so that's going to be 0.100 atmospheres squared times, and then the partial pressure of oxygen, which is the same, 0.100 atmospheres. And so when you calculate all of this out, your Q value becomes 4.00 times 10 to the 3. So 4.00 times 10 to the 3. Okay, so now that we have our quotient, we can use this. Temperature needs to be in Kelvin, and our temperature here, again, just to make sure, is 298. So then we plug this into our equation. So the delta G of the reaction is equal to the standard delta G, which is negative 71.2 kilojoules, plus R, which is the ideal gas law constant, and we're going to be using 8.314. So this is 8.314 and I want to say it's kilojoules. Let me double check. No, it's joules per mole Kelvin. So this is joules per mole Kelvin. And then we're going to multiply by the temperature, which is 298 Kelvin, multiplied by the natural log of Q, which we just found is 4.00 times 10 to the third. So here, Kelvin is going to cancel out there. So we have joules per mole. And so when we calculate this out, we get let's see, we're going to have to change this into joules. So this is 71,200 joules, and this becomes, give me a second, 20.5. So that's going to be, make sure, plus 20,500 joules. And so when we add these together, we're going to get about 51. Let's see, yeah, 50, negative 50.7, negative 50,700, or that's joules, or 50.7, negative 50.7 kilojoules. So that is the change, the delta G of the reaction under these non-standard conditions. And so as you can see, if we compare this with this, we can see that this is less negative, which means that under these non-standard conditions, the reaction is less spontaneous. It's more spontaneous under normal standard conditions. And so that's it for this problem. I hope you understood everything. I hope this made things clear. Hope you enjoyed the video. If you like my videos, please like, share, subscribe, hit the notification bell, comment in the comment section, and thanks for joining me. I'll see you next time.